guys, a very warm welcome to my channel. I am back to you again with a video. Now I am going to start solving chemistry questions of JBNSTS exam. So let's get started. Our first question is, name one technique which could determine the exact mass of the atomic nucleus. What is mass defect of an atomic nucleus? How it is related to the stability of a nucleus? So here is the answer. One technique that can determine the exact mass of an atomic nucleus is mass spectrometry. I don't know what mass spectrometry. Mass spectrometry is a powerful analytical technique used to measure the mass to charge ratio of ions. By ionizing the atoms in a sample and subjecting them to electric and magnetic fields, mass spectrometers can separate ions based on their mass to charge ratios, allowing for precise measurement of atomic and molecular masses. That's it. The answer of the second part. What is mass defect of an atomic nucleus? Mass defect. The nuclear mass M is always less than the total mass summation N of its constituents. The difference in mass of a nucleus and its constituents is called the mass defect. I hope you all know this formula. Delta M is equal to Zmp plus A minus Z into Mn minus capital M. So using Einstein's mass energy relation, we express this mass difference in terms of energy as delta Eb is equal to delta mc square. Here delta Eb is equal to binding energy, c is the speed of light, and delta m is the mass. In mass number range, A is equal to 30 to 170. The binding energy per nucleon is nearly constant, about 8 megaelectron volt per nucleon. The answer of the third part. How it is related to the stability of a nucleus. The mass defect is related to the stability of a nucleus through the concept of binding energy. The binding energy is the energy required to disassemble a nucleus into its individual nucleons. The greater the binding energy per nucleon, the more stable nucleus is considered to be. The stability of a nucleus is determined by the balance between attractive strong nuclear force, which holds the protons and neutrons together, and the repulsive electromagnetic force between the positively charged protons. So you see here the third part. So here is your second question. Number 12. Accidentally one of your mementos made with osteocell is fallen into a beaker full of vinegar. You observe that a colorless gas A is liberating at 200 to 210 degrees Celsius and under the 100 to 200 atmospheric pressure. Said gas A reacts with another gas B having pungent smell, forming a fertilizer C. Identify A, B and C and write the chemical equations. This question is divided into 1 plus 2 plus 2. Answer. The gas A that is being liberated when the memento made with osteocell falls into vinegar is CO2. When vinegar means acetic acid, and acetic acid's formula is CH3COOH, reacts with the calcium carbonate CaCO3 present in the osteocell. It produces carbon dioxide gas. The reaction between acetic acid and CaCO3 can be represented by the following chemical equation. CH3COOH plus CaCO3 is equal to CO2 plus H2O plus CH3COO whole to Ca. CH3COO whole to Ca, its name is calcium acetate. The gas B with a pungent smell that reacts with carbon dioxide A at high temperature and pressure is ammonia NH3. The reaction between NH3 and CO2 leads to the formation of ammonium carbonate NH4 which is commonly used as a fertilizer. The chemical equation for the reaction between NH3 and CO2 can be represented as 2NH3 plus CO2 plus H2O is equal to NH4 CO3. Fertilizer ammonium carbonate. If you want to get full marks in your JBNSTS exam, then you have to write chemical equations. Therefore, gas A is CO2, gas B is ammonia NH3, and the resulting fertilizer C is NH4 CO3. That's it. Question number 13. At the time of starting a car, the lead acid battery delivers roughly 50 amperes of current. Number A. During the 5 seconds that it might take to start the car, in total how many grams of Pb and PbO2 shall be consumed in the battery? We have to calculate the amount of Pb and PbO2. Answer. Typically, the current efficiency of a lead acid battery is around 85 to 95%. Let's assume a current efficiency of 90% for our calculations. Given data, I is equal to 50 ampere, T is equal to 5 seconds, Q is equal to IT. I hope you all know this formula. So here 50 into 5, so 250 coulomb. The current efficiency is 90%, therefore the effective charge passed 90% means 90 by 100, so 0.9 into Q is equal to 0.9 into 250 coulomb, so 225 coulomb. Then we have to calculate the molar ratio of Pb and PbO2. The molar ratio of Pb to PbO2 is 1:1. We know 1 Faraday is 96,500 coulomb. Moles of Pb and PbO2 consumed is charge passed by 96,500. The molar mass of Pb is approximately 207.2 gram per mole and the molar mass of PbO2 is around 239.2 gram per mole. So here we have to find the mass of Pb consumed is equal to moles of Pb consumed into molar mass of Pb consumed. So 2.33 into 10 to the power minus 3 into 207.2 gram per mole is equal to 0.4827 gram. Mass of PbO2 consumed is equal to 0.5573 gram. So during the 5 seconds it takes to start the car, approximately 0.4827 gram of Pb and 0.5573 gram of PbO2 would be consumed. So that's it. Now I am going to solve question number 14. Calculate the ratio of separation between successive 100, 110 and 111 lattice planes in a cubic cell. I think it is the easiest question for you. So let's solve. The ratio of separation between successive lattice planes in a cubic cell can be calculated using the Miller indices notation. We know D at the point HKL is equal to A by root over H square plus K square plus L square. Here A is a lattice parameter, HKL represents Miller indices of the plane. So D at the point 1, 0, 0 is equal to A by root over 1 square plus 0 square plus 0 square. So A D at the point 1, 1, 0 is equal to A by root over 1 square plus 1 square plus 0 square. So is equal to A by root 2. And the D at the point 1, 1, 1 is equal to A by root over 1 square plus 1 square plus 1 square is equal to A by root 3. So we have to find the ratio. Therefore the ratio of separation between successive 100, 110 and 111 lattice planes in a cubic cell is A is to A by root 2 is to A by root 3. So is equal to 1 is to 1 by root 2 into 1 by root 3. Simplifying this is equal to root 6 is to root 3 is to root 2. Question number 15. You are given following three complexes NiCN whole 4 2 minus, NiCl4 2 minus and NiCO whole 4. Can you compare their relative magnetic behavior? It is quite interesting. I hope you like it. Nickel complex's magnetic behavior. Let's analyze each complex individually. If you want to get 4 marks in your JBNSTS exam, then you can write highlighted point to grab teacher's attraction. Nickel complex's magnetic behavior. So number 1, NiCN whole 4 2 minus. In this complex, nickel is in the +2 oxidation state and it forms coordination bonds with 4 cyanide ligands. Cyanide CN- is a strong field ligand that leads to the pairing of e electrons in the d orbital of nickel. As a result, the NiCN whole 4 2 minus complex has a d8 or 3d8 electronic configuration with all electrons paired, and it exhibits a diamagnetic behavior. Here the Ni2 plus ion is sp2 hybridized. As it has no unpaired electrons in its orbital, so it is repelled by a magnetic field and do not possess any unpaired electrons. Number 2, NaCl4 whole 2 minus. In this complex, oxidation state of nickel is also in the +2 oxidation state. It forms coordination bonds with 4 chloride bonds. Chloride means Cl- is a weak field ligand which allows for the possibility of unpaired electrons in the d orbitals of nickel. The NaCl4 whole 2 minus has a d8, 3d8 electronic configuration similarly to NaCN whole 4 2 minus. However, due to the weak field nature of chloride, there is a possibility of unpaired electrons in the d orbitals of nickel. As a result, the NiCl whole 4 2 minus complex has 2 unpaired electrons, so it exhibits a paramagnetic behavior. This compound is weakly attracted to a magnetic field due to the presence of unpaired electrons. It is sp3 hybridized. So here's the formula of finding the oxidation state. Here we have to take nickel as x minus 4 is equal to minus 2, then x is equal to plus 2. Number 3, NiCO whole 4. In this complex, nickel is in the 0 oxidation state. As you can see in the top, x plus 4 into 0 is equal to 0, so x is equal to 0. And it is also sp3 hybridized. It forms coordination bonds with 4 carbonyl ligands. CO is a strong field ligand that promotes the pairing of electrons in the d orbitals of nickel. The NiCO whole 4 complex has a d8 electrons configuration with all electrons paired similar to NiCN whole 4 2 minus. Therefore, it exhibits a diamagnetic behavior and it is also repelled by a magnetic field. To summarize this total answer, NiCN whole 4 2 minus is diamagnetic, NiCl4 whole 2 minus is paramagnetic, and NiCO whole 4 is diamagnetic. Here 0 unpaired electrons, 2 unpaired electrons and 0 unpaired electrons. NiCN whole 4 2 minus structure is square planar. The structure of NiCl4 whole 2 minus is tetrahedral and NiCO whole 4 is also tetrahedral. So that is the answer. Question number 16. During electrolysis of aqueous solution of CdCl2, assume you use either platinum or mercury as cathode. Do you expect any changes differences in the cathode reactions in these two cases justify your answer. And second part is, what is the magnetic nature Fe2CO9? Justify your answer. This question is divided into 1 plus 2 plus 1 plus 1. Number 1. The electrolysis of an aqueous solution of CdCl2. Generally, the cathode reaction depends on the nature of the cathode material. In this case, considering platinum or mercury a cathode, we can expect differences in the cathode reactions. Let's analyze each scenario. Number 1. Platinum cathode. While using a platinum cathode, Cd2 plus ion reduces at the cathode. The half reaction for the reduction of Cd2 plus to Cd is as follows. Cd2 plus 2 electron minus is Cd. Cadmium 2 plus ions are present in the aqueous solution of CdCl2. Cadmium chloride. They will migrate towards the cathode and undergo reduction, resulting in the deposition of metallic cadmium on the platinum cathode surface. Next, mercury or Hg cathode. While using a Hg cathode, it is a metal and the behavior is different due to the unique properties of mercury. Hg or mercury is a liquid metal also, can form an amalgam with many metals including cadmium. Hence, the reduction of cadmium 2 plus ions at the mercury cathode would result in the formation of a cadmium amalgam. The half reaction for the reduction of Cd2 plus 2 cadmium in the presence of a Hg cathode is as follows. Cadmium 2 plus 2 electron minus and Hg, so is equal to HgCd. Therefore, when comparing the cathode reactions between platinum and mercury in the electrolysis of an aqueous solution of cadmium chloride, the primary difference lies in the nature of the product formed. While a platinum cathode, metallic cadmium is deposited, while with a mercury cathode, a HgCd is formed. And the second part of the question, the magnetic nature of Fe2CO9 is diamagnetic. Now I have to put justification. Here metal bond is present and the Fe2CO9 is 36 minus 34 by 2 and 2 by 2 is 1 metal bond. And the second reason is there is a bridging CO group. I want to tell about Fe2CO9. Fe2CO9, also known as iron non-carbonyl, is a complex compound consisting of iron and carbon monoxide ligands. Its magnetic nature is diamagnetic because iron has unpaired electrons in its 3d orbitals, and the presence of unpaired electrons can result in paramagnetism. However, in Fe2CO9, the bridging bond between the two iron atoms allows for electron exchange and coupling of the magnetic moments. As a result, the spins of the unpaired electrons align antiparallel, resulting in a diamagnetic interaction. Like, share and click the subscribe